Good morning again, everyone. Welcome back to our second catch-up slash question day. I did not see any questions sent to me via Piazza or email or what have you. So I was thinking that we could do a couple more simplex problems on the tableau, just to give a couple more examples and to point out what happens when we have an unbounded problem or a problem with multiple optimal solutions. So we can see that. And if you have any other questions that you want me to talk about or address, feel free to put them in the chat at any point, or speak up, whatever you want to do. So, unless anyone has something right now, then I think we'll just do another Tableau example. Alright. So let's think about this problem. So this is a problem that comes from this book, which is the old book for this class that's not readily available these days. And if you've got a particularly keen eye, you may see that this one has a slight problem. So let's go ahead. I'm going to put this in a Tableau and skip ahead of standard equality form. And we know we have two inequalities, so we're going to need two slack variables. And like normal, our slack variables will start off as the basis. One, negative 1, rather. 2, 1. We need to add a slack to this less than or equal to. So 1, 0. And we need to subtract a slack from this greater than or equal to. So negative 1. And 6. And remember that our non-negativity constraints are assumed in the Tableau format. Every variable is assumed to be non-negative, except perhaps for z, because that's our objective. It's not a true variable. And there's one other thing I forgot to do. forgot to negate the objective function row. Except that time I negated it too much. There we go. So we have an issue here. And that is, oh shoot. Thank you. I did not actually share the screen. There we go. This is where we are. This problem. Oh, thank you. I was going to do the whole lecture without showing anything at all. Right, so this is that problem in the tableau format that we explored a bit yesterday. But we have an issue. This is not in canonical form. This is in standard equality form, but we don't have an identity matrix anywhere. Right, S1 and S2 are supposed to be our basis, but we have this negative here. So it's not in its true canonical form. We can still find the solution, or the basic solution of our, where we are. It's fairly straightforward. S1 is 1, and S2 is negative 6. We'll address that in a moment. So what we want to do is get this in canonical form. So we're going to duplicate it. And all we have to do is row 3 times negative 1, which negates all of these. And we have our negative 6, which is what we determined the solution was up here. Now we're in canonical form. Now we can do a simplex iteration without worrying. But, like I said, there's a problem here. Negative 6 is negative. And we're assuming that all of our decision variables, including the slack variables, are supposed to be non-negative. So we're actually at an infeasible basic solution. Since S2 is less than 0. So tomorrow we're going to discuss the ways to actually move from an infeasible solution to a feasible one. But for now, what I want to do is simply disappear this little problem. What do I mean by that? Well, I happen to know. Well, let me draw the graph of the problem, or the plot of the problem. So if this is x1, x2, we have our first constraint is something sort of like that. second constraint is something sort of like that. And the origin is the basic solution we're at right now. Both of these are, by the way, are pointed in this way. So this is our feasible region. And we can see that the origin, which is the basic solution we're at the moment, is not actually feasible. So, like I say, tomorrow we're going to talk about how to navigate from an infeasible basis back to a feasible basis. But for now, I'm just going to point out that this point is feasible. This point is, or has the basis x1, x2. Right. So we're just going to pivot into that basis straight out of where we are right now. So that means we want to manipulate our top tableau to look like this. So that our identity matrix is under the x1 and x2 columns. We're going to do that by these row operations. Row 2 equals row 2 plus twice. Actually, let's start with row 0. Ooh, correction. Nope. Let's not start with row 0. We'll start with row 2, like I tried before. Plus twice row 1. So that gives us 0, -3. I'm going to write a temporary row 2 here. 0, -3. 2, 1, 6 plus, or -6 plus 2 is -4. And so that's our temporary row 2. And then we want to do a row 2 equals 1/3 row 2, which is going to get -1/3 row 2, which will put us in, have a 0 here, or a 1 here, rather, -2/3, and -1/3, and positive 4/3. Then we just do a row 1 equals row 1 plus row 2, and here this row 2 is this row. So maybe row 2 prime is helpful here. This gives us a 0. 1 minus 2/3 is 1/3. 0 minus 1/3 is -1/3. 1 plus 4/3 is 7/3. And then we still have to cancel out the objective row. So we're going to have a row 0 equals row 0 plus twice row 1 plus row 2. I'm going to call these prime, just for clarity. So I'm joining up a lot of row operations in one step because I am very comfortable doing these row operations. If you're not, I encourage you to list these all out step by step. At the same time, when we're doing simplex, we're not usually jumping to an entirely new basis. We're almost always exchanging, in fact, we are always exchanging one point in the one variable in the basis for one that's not in the basis. So we'll only be swapping one row, and the row operations are much simpler. The other way to do this potentially is if you feel more comfortable with the matrix multiplication format, you could use that if you wanted. I think it's kind of gross, so I use row operations. So anyway, here we were. These cancel out to 0. 0 plus 2/3 minus 2/3 is 0, which is odd. Is that supposed to be the case? No, because we have a positive one here and a positive one here. So this is actually supposed to be a minus. So we end up with 2/3 plus 2/3 is 4/3. Negative 2/3 minus minus negative 1/3 is going to be negative 1/3. And then we have 14/3 minus 4/3 is 10/3. So now we're in the new basis we wanted, x1, x2, which gives us the solution x1 7/3 or z 10/3, x2 4/3, s1 0, s2 0. And this is a maximization problem, so we've improved the solution. But more importantly, we're at a feasible extreme point, a feasible basis to the problem. Whereas before, we were at the origin, which was not feasible. Anyway, so now we can do a more traditional simplex iteration. So let's copy that and do what we did yesterday, which is find the smallest negative in the objective function row. Again, in our case, this is the only negative. And bizarrely, that has 2 negative values in it. Is that right? There's something wrong here. I've done something wrong, I believe. No? Maybe not. Oh, yeah. Yeah. Okay, we're good. So we pick S2 to enter the basis, and then we want to get our B over A for each of these. And we're going to find that these are all negative, or these are both negative. So what does that mean? Well, let me come back here and grab our plot again. Well, this this constraint is the second constraint listed there. So S2 S2 is the distance of our solution from the green constraint. So if we were to pivot and put S2 into the basis, that would mean that we are traveling in this direction along this constraint, away from the green constraint, because we're increasing our distance to S2. Now the problem is that there's no other constraint to stop us from increasing this indefinitely. We can increase S2 indefinitely. My spelling, this is one of those words that I can never, ever, under any circumstances, spell correctly. Gross. There we go. So we can increase S2 indefinitely. It has a negative coefficient in our objective function row. Which means that increasing S2 increases the objective. So this problem is unbounded. We can see that because our B over A So we found a variable to increase, but there's no bound on how much we can increase it because our b over a row column is entirely negative. So that's how we can identify an unbounded problem. So there's that. Are there any questions relating to that? All right. Well, just for just for kicks and giggles, well, just to demonstrate another property, let's suppose that, let me move this down a little bit more. Suppose that we had a positive here instead, and that this entry was 0. Now I don't know what problem would actually produce this tableau, but the thing is, every tableau with feasible solutions does represent some LP. I don't know specifically which one this represents, but some LP is represented here. Now, we're at an optimal solution. This solution, or this basis, is optimal because there are no negative entries in the objective row. So there's no variable for us to increase. However, or there's no variable that we can increase that will actually improve the objective function value. However, S2 is not in the basis. So we could swap S2 in without altering the objective function value. But S2 is non-basic. So we could, I'm not saying you necessarily want to do this, swap it into the basis. well, so let's do that. Our b over a is 7 and negative 4. We're going to ignore the negative 1. We're going to pick 7, so we're pivoting on this entry. So let's do that real fast. And we're going to end up with changing all of these. We're going to end up with a 1, 0, and we swapped out x1, so x2 is still in. 0, 1 in x2. That's what we want to end up with. So our basis has transitioned from, or will transition from x1, x2 to s2, x2. We can do that by r1 prime is 3r1, which gives us 3, 1, 1. R2 prime is, I'm actually going to use R1 instead of R1 prime here because we already have the 1/3. It's R2 plus R1, not R1 prime. So 1/3 minus 1/3, 0. Negative 2/3 plus 1/3 is negative 1/3. 0, 1 stays the same. 0 plus 1 is 1. And I neglected to change the objective functions. So I multiplied it by 3, so that's 7. And I added 7/3 to 4/3. It's going to be 11/3. So now we're at a new basis, a new optimal solution. And notice we didn't change the objective function row because there's already a 0 in that entry. So we don't have to alter that to get our identity matrix that we're looking for. Which means that the objective function value remains the same. In other words, there are multiple optimal solutions. And that is all because there was a 0 in one of the non-basic columns. And there was no negative entry in the objective row. There was nothing we could do to improve the solution, but we could skate back and forth and translate on between two equivalent solutions. So that is 2 points that I didn't get to talk about yesterday. And if no one has any questions, I think I will try to find a problem to solve on the tableau, just so we can get another example. All right. I need to find one that's not too enormous. To find one with 3 variables. Okay, we'll do this one. This is one of the problems from the homeworks from last semester, right here. So let's give it a spin. Let's write the problem in standard form first. My marker is much bigger than it was. Still a little big. Oh well. Uh, x1 plus, what do we need here? Plus a slack equals 4. 2x2 plus another slack equals 12. So that's standard form. Well, we also need our x1. We need our negativity. That's important. And then let's convert that to a tableau for us to solve. Make that one smaller too. Z, x1, x2, s1. I need a longer line. It needs to be lower down. Bingo. So Z column is always 1 followed by zeros. We can look up here at our standard equality form to get our A matrix. 0, 2, 0, 1, 0, 3, 2, 0, 0, 1, 4, 12, 18. With 3, 5, 0, 0, 0, and 0. Is my microphone coming through? Yeah, it is. Maybe? I just got an error saying that it was having trouble detecting it. Okay. Good. Thought I'd been talking without my microphone. So, is this process clear enough? Is anyone struggling to understand where I've pulled all of these numbers from? Well, they're just the coefficients of the equations in our standard form, including the zero coefficients, which are invisible up there in our standard equality form version. They've been ignored. So, oh, there's one thing I forgot to do. Very important thing. I forgot to negate my objective function. So now we can begin. Let's make this smaller as well. Well, x2 has our smallest negative entry. So we're going to pick that one. And then our b over a is 4 divided by 0. That's undefined. 12 divided by 2 is 6. 18 divided by 2 is 9. So we're going to pick 6 is our smallest positive number, which means that we're pivoting about that point. So now we no longer need anything up here, so I can scoot down here and copy our tableau. So we're pivoting around that point, so we need to change that to match up with that. And I'm just going to erase all of these, even though these will not be changing. It's maybe just a little bit cleaner to rewrite the whole thing. So the first thing we're going to do is R2 prime equals 1/2 R2. So we end up with this row. Then we can start eliminating other rows. There's already a 0 here, so row 1 does not change. We don't need to touch row 1. About row 3, why am I writing that up there? I've always written it on the side. I'll get confused. Then we will have row 3 prime is row 3 minus row 1. Which is going to give us 3 stays there, a 0, a 0, negative 1, 1. 18 minus 12 is 6. Finally, we need the objective row. So row 0 prime is row 0 plus 5 times row 1 prime. Using the prime here because 2 doesn't divide into 5 easily. So I'm just going to use our unit row instead. So -3 doesn't change because of that 0. -5 turns into 0. 0 is unchanged. 0 plus 5 halves. 5 times 1/2. 0. And then plus 5 times 6. That's 30. So there we go. We've done our first pivot. So our next pivot, there's only one negative entry in the objective column, or the objective row, rather. So we're going to pivot on x1. Let's get our b over a. It's going to be 4 divided by 1. 6 divided by 0 is undefined. 6 divided by 3 is 2. 2 is our smallest positive number. So we're going to pivot on 3. For our sanity, I will erase the old pivot. So let's duplicate that. Ooh. Got a little wild, got a little wacky with my selection. There we go. So let's erase all of the entries. And we're going to be left, we want this. So we're going to start with row 3 prime is 1/3 row 3. Turn that 3 into a 1. 0, 0, negative 1/3, 1/3, and 2. We don't have to alter row 2 at all because there's already a 0 there. So row 2 stays the same. Row 1 though, we're going to have row 1 prime is row 1 minus row 3 prime. Gives us 0. That's unchanged. That's unchanged. 0 minus negative 1/3 is positive 1/3. And that's going to be negative 1/3. And 6 or 4 minus 2 is 2. And then we're just left with the objective row. We've got a negative 3 up there and a 3 here, so that divides in evenly. So I'm not going to use the prime. I'm just going to say R1 plus R3, not prime. Unchanged, unchanged. 5 halves minus 1 is 5 minus 2 is 3 halves. 0 minus 1 is negative 1. And 30. Oh, wait, that's a positive one. I'm adding a positive one. I got confused with the negative. So that is a positive one. 30 plus 6 is 36. And that looks like we're done to me. Except I missed a 1 there. So our final basis, let's try to extract our final basis from here. So z is sort of implicitly in the basis. So you could start with z if you wanted, because it has the first entry in the identity matrix. Then the second entry in the identity matrix is here. S1 is that column, and then x2 and x1 is the basis we have. In that order. Now, you can reorder the basis if you wanted, just by swapping 2 rows. But there's no real reason to do that. So instead, we're just going to pull out the optimal solution, 36. X1 is 2. X2 is 6. S1 is 2. And S2 and 3 are non-basic, so they take the value 0. So that is our solution to this problem. Does anyone want me to do anything else? Talk about anything else we've done in class? Anything at all? Alright then. I think that's enough for today. So I'll stick around for a little while. But you guys are free to go.